Yeah, I'm good.
We figured I would start by giving a little overview of some of my research. And the big question here is, what can crystallography and mineralogy teach us about biominerals? And then at the end, I'm just going to do a quick highlights reel of what we've recently brought into the National Collection. So I want to start by just giving us a minute to bask in how amazing minerals are. So I feel very lucky that we are getting to speak today because you are a group of mineral enthusiasts. And I would say that unfortunately, most people on this planet don't realize just how important minerals are. I was lucky that in 2021, I went to the GSA conference. This is the conference for the Geological Society of America. And their president at the time happened to be Barb Dutrow. She's a professor at LSU, and she wrote the Manual of Mineral Sciences, the textbook that all of the intro mineralogy students use. And so Barb used the opportunity for her presidential lecture to really give an ode to minerals and mineralogy. So I think a lot of people see us as a science that's no longer relevant, when in reality, minerals are the basic building blocks that build our solid earth. And so I took away a few quotes from her talk, and the big one was that mineralogy is a core science. And that really stuck with me because it's really at the center of most of these other fields that we think of as being rather independent. But instead, mineralogy is a way that we can translate between seemingly disparate fields. So obviously, petrologists care about mineralogy. Obviously, geochemists care about mineralogy. But what about the medical sciences, biology, material science, geochronology, environmental science? All kinds of different sciences truly depend on minerals. They are the subjects of their research. But unfortunately, a lot of people don't realize this, and so they'll often study these minerals without actually studying the minerals. So they'll study the biology that surrounds biominerals, for instance, but they won't actually take that mineralogical perspective. So because you are mineral enthusiasts, I feel like I can say this to you, that it's really, really important to remind people how important minerals truly are. And so I like to start some of my talks, especially to more general audiences, audiences with children. I like to tell them, minerals really do matter, and mineralogy is a growing and still very, very relevant field. And so we'll recap again. We all know this, but I think it's always helpful, even as an experienced mineralogist, I find it helpful to remember exactly what a mineral is supposed to be, because sometimes we end up with these oddball examples and we have to remind ourselves. So a mineral, first and foremost, is solid, right? So no liquids, no gases. It's a crystal. So it has a repeating atomic arrangement. It's chemically consistent. So this is something where we sometimes end up in issues where if you change some of the chemistry, but not all of it, it has to be consistent from the same mineral to the same mineral. And of course, minerals are also naturally occurring, so it can't be something that's only made in the lab. And they are considered to be something that's inorganic, so not related to biology in any way. But I have kind of come full circle. I was actually raised by two biologists, and I always told myself that I would never do biology. I'm going to be a mineralogist. I'm going to be a geologist. And lo and behold, I ended up becoming a biomineralogist. So today we're going to talk about biominerals, which are minerals, as Cindy mentioned, that are here thanks to organic metabolisms. So I like to think of it as if the mineral exists here and it wouldn't exist if biology didn't exist, then I would consider it a biomineral. And so the most obvious trait of biominerals is that they tend to look a little different. So we can compare a geologically formed apatite crystal on the left to bone, which is bioapatite. So all of us are biomineralizing organisms. We all have bones, thank goodness. And these bones look very, very different, morphologically speaking, from a crystal of apatite. The same can be said for aragonite. Aragonite crystals in geological settings look distinct from mollusk nacre, for instance, that we find in pearls, or the interior of a coral skeleton. And so on various scales, we find that biominerals can look different. It turns out that oftentimes, not always, but oftentimes, biomineral physical properties can also be dramatically different. And what I mean by that is I like to use this an analog or this analogy of wood and glue. So wood on its own is a very strong material. We use it for construction and whatnot, but you can actually split wood fairly easily, right? It splinters very easily and you can, hack away at it with an axe. Now, glue is a very, very, very different material. It's a gloopy, sticky liquid. And so they are nothing alike, wood and glue. But if you put them together and you orient the wood in specific orientations, you end up with plywood. And plywood is not just like wood. Plywood is actually stronger than normal wood, and it has this added flexibility from the glue, which makes it a compound material with added benefits. So in a way, it's like a more superior material compound. And so biominerals oftentimes will work in the same way. So I like to think about apatite. Imagine if your legs and arms, the bones in your legs and arms were made up of pure apatite crystals. We know that apatite has very strong cleavage, which means it has these planes of weakness that if you were to hit it with a hammer or a strong impact, you could literally break that crystal in half. So that would be really, really bad if you're going about your daily life, you fall, or you get hit with something and your bones would literally just cleave. Imagine that. So unfortunately, bones can still break, but for the most part, they're incredibly strong compared to their apatite counterparts. And so bone is actually made up of collagen and proteins and all kinds of other organics. And the crystals themselves are arranged in these highly, highly organized and very complex networks. And so I don't actually study bone myself. I find it incredibly complicated. So I'll be looking at some slightly more simple examples today. But just something to think about, that how amazing our bones are and how amazing we are biomineralizing as humans. So I also like to point out that biominerals are really everywhere. Everywhere you start looking, you'll start to notice them. So obviously us humans and all other animals on the planet that have vertebrae or vertebrate animals create this bioapatite. But also corals will make their skeletons out of aragonite and calcite, as our bivalves will also use aragonite and calcite. But we also have plants. Plants will make phytoliths, which are these little structural elements made up of amorphous silica. So like an opal structure or glassy-like structure. So not quite a mineral, but close. We also have diatoms, we have coccoliths, snails, all kinds of interesting animals around the, and just organisms in general in the tree of life. And so today I'm going to take extra care to talk to you about biocarbonates. So biocarbonates would be things like aragonite and calcite that are formed by organisms like corals and bivalves. And they tend to get a lot of extra attention in the biomineral community because they are so important for thinking about how carbon gets stored in our biosphere, and they're just so common. So there are many, many organisms that can actually make biocarbonates. And so back to our biomineral definition on the left, I said it has to be crystalline and chemically consistent. And so if we look at the different types of polymorphs or different ways in which calcium carbonate can arrange itself, we can have several different minerals that form. So calcite and aragonite are like precise polymorphs in that they have the same exact chemical composition. They're both calcium carbonate, but calcite has a different crystal structure than aragonite. And so then if we were to add a little bit of water to that, we would end up with vaterite, and a higher magnesium concentration can give us dolomite. So these are ways in which, very similar chemistry overall, but maybe different structures. And these are all minerals that are commonly found in biocarbonate forming organisms. So we're going to be talking primarily about aragonite today, but I just wanted to point out that there are other biocarbonates out there. And at the bottom, I have what I call the unit cells. So these are the smallest possible building blocks or tessellations that it would take to build a crystal of, say, calcite or aragonite. And they are all composed out of the different chemical compounds, so calcium and then carbonate. So carbonate, in this case, are those little tiny triangles that have oxygen and carbon, and they're the red and gray triangles that you would see there. And that we're going to come back to that in a minute. So who exactly is forming these biocarbonates? So the ones in red are all these different groups in the tree of life that can form carbonate. And so here are some of them, images of some of these. And so the next big question is, now that we know that all these different organisms can form carbonate, how are they forming it? How are they forming these minerals? And so Cindy mentioned in my intro that I said some of them are happy little accidents and some of them are very controlled. And so when we talk about biominerals, we tend to separate them in terms of induced biomineralization, which are essentially accidental minerals that are formed thanks to a byproduct of a biological metabolism. So let's say that you're a bacterium and you're eating things, and for some reason you happen to concentrate calcium and carbonate in a local environment due to your life business, then those ingredients are there and can precipitate calcium carbonate potentially by accident. So that would be what we consider induced biomineralization. So without the organism there, the carbonate wouldn't exist. And so, it's still a biomineral. Now, on the opposite end of the spectrum, we have very controlled biomineralization. So these are things potentially like mollusks or echinoderms, organisms that are specifically making shells or any type of housing for their body. And they're using minerals in a very precise and ordered way. So they're trying to make these minerals. And oftentimes they will use all kinds of really interesting formations, mechanisms to form these crystals. And so I did a word cloud of some of the abstracts that were submitted to a session that I'm organizing with a former student of mine and some of my colleagues. So we have the Goldschmidt Conference will be happening in August in Chicago. And so we're going to have a whole session to talk about biominerals. And these are some of the words that came out of these abstracts. So we have crystal growth and biomolecular templates, ACC, which stands for amorphous calcium carbonate. All of these topics are really, really important in this field of biomineralization, especially biocarbonates. So why do we even care about these in the first place? So I would say that there are many, many, many reasons why we should all care about biocarbonates. First and foremost are that they really impact the health of organisms and world ecosystems. So coral reefs alone are incredibly important for life on Earth. And so they take up less than 2% of the ocean's floor by area, and yet they help to support over 25% of all marine life. And so without coral reefs, you don't have nurseries for fish, you don't have tourism for many island nations, and you also lose coastal protection from hurricanes and other storms. And so these are reefs that are very important, and they're formed through minerals. They're formed through biocarbonates like aragonite. We also know that they can be farms essentially to find new pharmaceutical compounds like antibiotics, and they serve as a way for agriculture. So not just coral reefs, but other aquaculture depends on biocarbonates forming nice and strong. So for instance, here I have an oyster shell. So oysters obviously form their shells from calcite. And so imagine if the calcite isn't looking so great, you might end up with some wilted oysters. The other reason why we all care about biocarbonates and bicarbonate minerals is that they're very intricately linked with the carbon cycle. So calcium carbonate has carbon in its formula. And so when it comes to the cycling of carbon into the rock record and on the surface of our planet, we really have to think about these biomineralizing organisms and how they're making these carbonate minerals, which could potentially store carbon on longer timescales. And tied with this, we care a lot about ocean chemistry and ocean acidification, which you may have heard about. And so in the environment, carbon cycling and biominerals are intricately linked. And this leads us to thinking about biominerals for paleoproxy studies in climate science. And so in the past, 50 years or so, or even longer, scientists have been using coral cores and shells and otoliths and all kinds of biominerals to use as almost like libraries of what happened in the past. So as these organisms grow their skeletons and shells, they grow them in layers, and these layers can essentially trap information from the environment at the time in which those crystals grew. And so it's an incredibly powerful way to look at past chemistry, past ocean chemistry, and translate that into real life events. So what was the temperature like at the surface of the ocean? What was the carbonate chemistry like? And what was the salinity like? So all of these can be essentially proxied out through these biominerals. And of course, paleontologists love biomineralizing organisms because they fossilize very well, very easily. They're hard parts, and so they tend to be preserved much more easily into the rock record. And finally, this is one that I really like, this idea that biominerals have very interesting material properties and they can inspire technologies. And so we know that, for instance, nacre is incredibly strong. It's, I think, thousands of times stronger than aragonite on its own. And so thinking about how we can produce new materials in the future using inspiration from nature. And of course, they also make luxury goods like pearls. This here is the Pearl Dun necklace, which is a Cartier necklace. It's part of the National Gem Collection. And it's obviously a very, very valuable piece of jewelry that helps us appreciate biominerals. So today I've highlighted in green some of the things that will apply to the topics we'll talk about today with environmental biomineralogy. So I like to think of the interface between the environment and these biominerals as they form. And so what exactly is environmental biomineralogy? It's quite a mouthful. Well, it's more of an interdisciplinary approach to studying minerals. And I think that it's going to help us better understand our environment. And so it really is a cycle between the environment, the geochemistry that's recorded in the environment, the crystals themselves, back to how organisms are forming these crystals, and back to the environment. So it's really a cycle. And yet, I would say that only these two parts of the loop have been studied. So we have a lot of scientists, environmental scientists, spend a lot of time thinking about records of the environment. Geochemists, will dedicate their lives to learning about trace element paleoproxies. And of course, biologists want to know this interface between the environment and shells, or the environment and the biology of the organism that lives in the mineral shell. But not very much attention has been paid to the minerals themselves. And so I'm going to argue that we need to do a better job at just measuring the minerals, doing some mineralogy. And this is all very basic science. So I'm going to walk us through a couple examples of what this would look like. So the first is looking at coral aragonite crystal structures. And the second is looking at pearl nacre geochemistry and mineralogy. So we'll start with the corals. So I mentioned that coral reefs are incredibly important. And what we know about them so far, beyond their ecosystems and how they work to grow colonies of coral, and if we look at a smaller and smaller scale, we know that corals are essentially like little tiny jellyfish that are upside down. So they're in the same group as jellyfish. They have tentacles, they have a mouth and these tissues, but corals will grow aragonite skeletons under those tentacles. And so this we call a polyp. And if we were to slice one open, we would see that there's the skeleton below the tissue layer. Biologists have also begun to do some work on how these coral skeletons grow. And so the predominant theory is that the organism can take in seawater from its environment. It can pump out and pump in specific ions that will help it essentially precipitate crystals as if it were the same situation as a beaker, where you could, as a chemist, you could throw in all the ingredients and precipitate your crystals. So that's one theory. On the other side of the scale, we have people that think that biology is controlling everything, and that with a few biomolecular templates, like specific proteins, that the aragonite will just precipitate no matter what conditions are around it. So there's actually a very hot debate going on right now in the biomineral community about how corals build their skeletons. It's a surprisingly simple question, and yet it's still up in the air. And so this is where I come in, and my group comes in, and we're thinking about, well, we know what the crystals look like morphologically, right? A lot of people have done SEM studies, but no one has really thought to think about the actual crystal structure. So that unit cell that I mentioned earlier. So our unit cell, smallest building block of aragonite, we can define it as A, B, and C axes that make up a box. And this box surrounds calcium and carbonate ions. So we'll be going into more detail with this unit cell, but just keep in mind we have A, B, and C axes, and together they make a box with a specific volume. If you see the scale bar on the side, that's 1 angstrom. So this is really, really tiny. We're thinking about a very small scale. And so my big question is, what can the end products of biomineralization, in other words, the crystals, tell us about the conditions during crystallization? So how did these corals essentially form these crystals of aragonite? That's a big question. So to answer this, I collaborated with many, many different groups of coral scientists who had access to corals that had grown all around the world. We have deep sea corals that were grown at very deep environments, some of them as deep as 5,000 meters below the surface. So these are not your typical tropical corals that we think about. And then, of course, we also have our shallow water corals, which are our beautiful tropical reefs that we're all more familiar with. And so for the rest of the talk, I'm going to be bringing out my mineralogy geochemistry toolkit. And so these are instruments and different methods in which we do mineralogical studies. And I like to think of them as we have different sources and different things that we're trying to achieve. So we tend to use X-rays, lasers, and electrons. That's what I always tell my students. I'm like, we're using X-rays, lasers, and electrons. We're shooting one of those 3 things, and then we're using an instrument to collect information in the form of other X-rays, other light, or other electrons. So it's actually fairly simple. We just have to know which tool to use when. And then for chemistry, we can use bulk chemistry by dissolving things using ICP-MS, so inductively coupled plasma mass spectrometry, and or we can do stable isotopes and think about isotopes. I'm not going to talk about isotopes very much today because it takes a long explanation, but just think of it as a fancier form of chemistry if you're unfamiliar with them. Okay, so my favorite tool in our department is the micropowder X-ray diffractometer,
there was this talk.
Hello? Okay. So our XRD at the Smithsonian is on the left. I have nicknamed it MOMO because it uses molybdenum X-rays. So we're using a single source of X-rays with a single wavelength, and therefore we're able to determine our structure. So let me go into that a little bit more. So here we have our molybdenum X-rays. They hit our crystals, and our crystals are going to be oriented in many different ways because I'm using a powder. So some of the crystals will be oriented in the way that you're seeing them here. Others will be tilted off to the side. And so all in all, you're getting all of the possible orientations of a crystal, and they're going to diffract X-rays. And those X-rays will hit an imaging plate or a detector, and they'll look something like the blue box in the middle. And so those rings are actually individual X-rays that have bounced off of our crystal and landed on our detector. So the distance between those rings essentially is giving us information about the distance between different crystallographic planes. And if we take that data, we integrate it together into that cone and turn it into a line, we get the classic X-ray diffraction pattern. So this is what everyone talks about when they say, oh, did you ID that? The mineral identification, this is the premier way to identify a mineral. So obviously you're all experts and you might be able to identify visually, but let's say you're handed an obscure mineral and you have no idea what it is. This is the tool that a mineralogist, especially a professional mineralogist, would use to tell you exactly what that mineral is. So we know that there are almost 6,000 described minerals on our planet today, and there are probably, up to 9,000 that haven't even, or total on the planet. So there are many that haven't even been described yet. And so each mineral has a unique pattern. So we think of it as a fingerprint. And so we have very, very extensive databases that allow us to match the diffraction pattern of an unknown sample with a known sample. So it's a very, very powerful tool. It's a very old tool, and yet it still does wonders today. But I'm a crystallographer, and so I already know that we're looking at aragonite, right? Corals are aragonite. I don't need XRD to tell me that. What I need to know is the size of that unit cell. I'm really interested in more than just the mineral ID. I want to know more about the crystal structure. And so we're going to use a program that allows us to do Rietveld refinement analysis. And this is just a fancy way of saying we're going to take a known structure of aragonite that has known A, B, and C axis lengths of our unit cell, and we're going to take our unknown aragonite and fit them together and essentially get values for our unknown. And this is what we get. This is my coral data. And what we find is that if we have unit cell volume, so A times B times C on the y-axis, both our deep sea and shallow water corals are pretty similar to one another. So these are all different corals. And the one on the far right is values from previous studies. So mine are a little bit longer, but there are only 1 or 2 previous studies that have ever done Rietveld analyses for corals before. So this is a really important study because it really helped to expand our data for corals. And not only that, but we're able to show that between deep sea and shallow water corals, there are some nuances in the crystal structure. So even though the volumes appear to be, pretty similar all in all, if we start to dissect one axis at a time, we find that the A and B axes are actually consistently and significantly different from each other, from the deep sea to the shallow water environments, which to me says that there could be a difference in how they're forming, even if it's on a very tiny scale. So we're going to add a little chemistry from our toolkit, and we're going to see what exactly is in these crystals that's making them different. And so it turns out that we can correlate some of these shifts in our axis lengths with various trace elements. So trace elements are elements that are in our crystal structures, but it's not enough to really change the mineral, right? So we're not talking about a strontium carbonate or a magnesium carbonate. We're talking about calcium carbonate that has just a little bit of magnesium on the millimole scale. And so here we're clearly seeing that A-axis lengths seem to be positively correlated with boron and strontium concentrations, and potentially negatively correlated with magnesium concentrations. And so these trends are really important because this is the first time that we're really thinking about how trace element chemistry, and more importantly, some of these trace elements that are used for paleoproxies to learn about climate, how are those linked to the actual crystal structure of our corals? And how can they change over time and with different conditions? So this was my first paper looking at this. And since then, we've done a lot more work to tease out some more details. And I'll talk a little bit about that later. So this is an example, like visually speaking, of how this would change. So calcium is in blue. Strontium is very similarly sized to calcium in terms of its ionic size. Manganese is a little smaller. And then you'll see that magnesium is a really small ion. So it's going to really shrink that unit cell. And so this is obviously the pure end members. But imagine if you have a bigger crystal and you're stuffing in different trace elements, you might expand in some cases and contract in other cases. And so we're very curious about how together they end up changing our unit cell. And so one way to think about this is to compare our corals with other aragonites. And so we have access to some mollusks, which are other bioaragonites, but also some synthetic aragonites and geologically formed aragonites. So we're going to go back to our X-ray diffractometer and measure the same thing, but with our other forms of aragonite. So it turns out that mollusk aragonites are quite different from coral aragonites. I don't have as many of them here, but I would say that for the most part, they seem to be smaller in terms of their unit cell volume. And we know that their morphology can be quite distinct from coral crystals on a very small scale. And I'll show you some more pictures later. Then we took some synthetics. So we did some aragonite experiments, my colleagues did. First, they did some synthetics where they took seawater, like you would in a coral. They put it in a beaker, added other ions, including calcium and carbonate, and were able to precipitate aragonite. And it turns out that this aragonite is almost identical to the coral aragonite that we see, which is pretty amazing, considering that one of the theories for coral biomineralization is that it forms similarly to a beaker. So this would point to that as well. Whereas a freshwater synthetic, what I mean by that is that they essentially took a beaker, put in calcium carbonate, but they didn't add in all the other salts that you would find in seawater. And those aragonites made much smaller unit cell volumes, and they're very, very similar to geologically formed aragonites, which have much, much smaller unit cell volumes. And so using maps like this or plots like this, we're able to really see that there are differences between aragonites formed by different methods. And so this hopefully can give us some more clues as to how corals form their skeletons. And again, when we look at nuances between each of those individual axes, this pops up even more. So we know that mollusks tend to have shorter B-axis lengths than corals and even geologically formed aragonites. And so it can get really, really interesting, and we can spend a lot of time thinking about, okay, this is getting shorter, this is getting longer, why is that? And so we're going to turn now to Raman spectroscopy to give us some more clues, because one of the theories that a former scientist came up with in like the late 2000s was that perhaps mollusk aragonite has an overall larger unit cell volume compared to geoaragonite, but they said, well, it could be organics. You know, that's the obvious difference. You have biomineral versus a not biomineral. So let's measure organics. And one way we can do that is by looking at the background of our Raman spectrum. And so here on the left is a typical Raman spectrum, where we have intensity on the y-axis and increasing Raman shift on the x-axis. So these are peaks that are essentially bonding environments of our carbonate groups in our crystal structure. And then this bump is what we're actually curious about. So normally it should be perfectly flat if there are no organics. But if there's some kind of luminescence or fluorescence in our sample, we'll end up with this background. And we're going to assume that the background is only due to organics. And so if we plot the amount of organics or the amount of that fluorescence as a function of our volume for our unit cell, we find that mollusks have a ton of background fluorescence. You know, their intensity in arbitrary units is, you know, in the thousands, whereas corals have barely any background fluorescence. Their backgrounds are very, very flat. And so this tells me that, well, even though corals we know have even larger unit cell volumes, right, than mollusks, it's probably not driven by organics. So let's go back to chemistry and compare some of the trace elements. And so preliminary studies show that it could actually be some trace element incorporations that could be driving at least some of these unit cell shifts. And so here we've plotted volume as a function of strontium and boron. And sure enough, there seems to be a positive correlation where the corals are up here and mollusks are down here. So corals have more strontium, more boron, so more incorporations overall. But of course, it's actually quite complicated. And so we're going to have to look at this more carefully in the future. So just as a sanity check, we're going to do a little bit of imaging of electron microscopy. And so many of you know Tim Rose and Tim Gooding, and so they're very kind to help me with some SEM work. And we were able to look at various morphologies of these crystals. So this is actually work done by other folks, but I just wanted to show this is the type of imaging that we could do. So this is an image of nacre, which is from a mollusk. So this is the same like mother of pearl material. And look at how the crystals are almost like little pancakes, and they're stacked like bricks. Whereas corals form these crystals that kind of just radiate out. So these are acicular crystals. And so they look very distinct, morphologically speaking. But as mineralogists and crystallographers, we know that even though something can look different, it doesn't mean that it's actually different crystallographically. But in this case, we actually did the opposite. We started with the crystals, and now we're looking at the morphology. When in fact, the synthetic aragonites that were precipitated from seawater, so those beaker ones, they look pretty similar to our coral aragonites. And so the conclusion here is that maybe rather than having to do very complicated studies with corals, where you have to grow corals in tanks and they're really, fragile and can die easily, why not, at least for starters, use beakers, precipitate aragonite, and learn something about different environmental shifts using this much simpler system as an analog. So to conclude on this project, I would say that the big takeaway is that corals are not as controlled, or they seem to be more on the induced side of the biomineralization spectrum, whereas mollusks, I would maintain, are still on the controlled side of the biomineral spectrum. So they form in very different ways. I think that's the big takeaway here, even though they're both aragonite and they're both biominerals. So what can the end product, what can the crystals tell us about biomineralization? So we see that X-ray diffraction, or thinking about crystallography, can show us that there are differences between different aragonites, and that there are shifts that seem to be sensitive to trace element incorporations. At least they're correlated. And it's likely that coral crystallization is tied to geochemistry as opposed to organics. And beyond the morphology, we find that mollusk aragonite is crystallographically distinct from coral aragonite, and so they likely formed by very different mechanisms. And finally, I'm going to suggest that we start using seawater synthetic crystals as reasonable analogs, at least for starter studies. So the next step in these future studies, now that we have a little bit more understanding about coral crystallography, is thinking about how environments can be changing very rapidly, whether it's ocean acidification or storms, pollution, or other shifts in environmental and local chemistry. And so thinking about how do all of these shifting environments impact biominerals, from dissolution of skeletons, decreased rates of calcification or growth of new skeleton, breaking of skeletons, so thinking about those material properties again, and just making things that are a little bit more emaciated than we would expect. And so to work on this, I had an excellent student who worked with me at the Smithsonian as a Robert Heavey Fellow, and she was actually looking at how coral crystallography can couple with very precise geochemical measurements. And so this is work that we're actually writing up right now, so I won't share it, but in the future, I have some pretty exciting results to share. The short story is that, yes, they are linked, and it's going to be really interesting to follow that into more studies and looking at how different environmental parameters can affect this. So now that we've talked a little bit about corals, I wanted to take a moment to think about pearls. And I really like studying pearls because they are biominerals, but also they're gems. And as a curator of gems and minerals, I think it's a really great way to combine all of my loves into one project. And so this project actually was started by the Gemological Institute of America. They have close ties with a pearl farm in Tennessee. And so Kentucky Lake is an area that straddles Tennessee and Kentucky. And there's a family there that has been culturing pearls, so essentially farming pearls, for a couple of generations now. And so for those of you who are unfamiliar with what a cultured pearl is, These are pearls where essentially you take a mussel and they do a little microsurgery and they insert a bead made up of aragonite from another shell. And they then put them in these cages and they plop the shells back into the water, in this case, an area around Kentucky Lake, and they let a pearl grow over the course of 2 or so years. And so the pearl will grow layers over time. And then when it's done growing, they will go and they'll harvest the pearl out of the organism. And sometimes this process can be repeated a few times with the same mussel. But this one obviously reached the end of its life because they cracked it all the way open. So that's how cultured pearls are made. So you're not starting from scratch. This is not a natural pearl where you would have a natural irritant, like the stereotype is a grain of sand. Usually it's a piece of organic or something. So this is to illustrate it a little bit better. You have a beautiful pearl. Let's say that this was a cultured pearl. You would have your irritant or nucleus, and then the nacre would form in concentric layers around this beautiful round surface. And if you were to zoom in under scanning electron microscopy, you would see those platelets that I talked about earlier with nacre, where essentially these platelets are aragonite, they're crystals of aragonite. It's actually interesting, they're stunted along the C-axis, so they grow longer along the B and A axis. And the organism can use these biotemplates, these chitins and proteins, to essentially direct how it would like the crystal to grow. So it poisons the surface and it lets the sides grow. So it's really, really amazing engineering by the organism to create this material. And so this was a great project because it was started by GIA, and they had these pearls that they had sliced open, and I'll show you that in a second. But the key part here was that it happened to be near Kentucky Lake. And Kentucky Lake has a long-term monitoring program that's been going on for over 40 years. And so it's run by Murray State University, which was actually my father's alma mater, which was a fun little fact. And they have been measuring temperature, pH, total alkalinity, sulfate, any environmental parameter you can think of. And so as an environmental biomineralogist, I thought, well, wouldn't it be great if we could take all of these environmental parameters and essentially map them onto these pearls that GIA had started working on? And so this was during the pandemic, and we were all very, very limited as to what we could do. And so we decided, yes, we're going to try this. We took the environmental parameters that we knew of, and because these are cultured pearls, we know the date of implantation and we know the date of the harvest, right? So essentially we know the time frame from here to here. And so we did just that. We used this as essentially an environmental time capsule. But our pearls weren't perfect. Our pearls are actually Keshi pearls. So Keshi pearl is a funny way to say an accidental pearl that was formed during the culturing process where the bead fell off. And so essentially it's just a little tiny bit of organic material was its own nucleus. So it forms these kind of funky looking pearls. They're not round like you would expect. And so if you slice one open, you would get something like this. And so this is a centimeter scale bar, so they're quite small. So this is only a few millimeters across. And so here is our nucleus, and then you would have one side and the other side, A and B, should be mirror images of one another. So the pearl is forming around that nucleus, even if it's kind of a wonky shape. And so this project started with GIA and Wisconsin. And so they had done this beautiful transect collecting oxygen isotope data. And so this was done at the Sims in Wisconsin, and essentially each of these little dots is a data point where they essentially ablated a small amount of the material and were able to measure for oxygen isotopes. And the reason that they did that was that A, it was the first time that they were ever measuring oxygen isotopes in nacre or in a pearl. And B, they knew approximately the temperature of the lake because they had the Kentucky Lake water information. And so this is a bit of an expected result. We know that oxygen isotopes are negatively correlated with temperature in a water system. And so this was a really great, sanity test for us to say, yep, it also works in pearls. Pearls aren't doing anything all that different. They are faithfully recording the temperature conditions in Kentucky Lake. So, that's cool, but it's not enough to really publish a paper. It's like more of a factoid rather than full story. And so that's where we went. I went back to the Kentucky Long-Term Monitoring Program and I said, what else can you give us? What other environmental data can you give us? And what can I do at the Smithsonian to add to this mineralogical data set? And so I actually turned to Carnegie down the road because I wasn't allowed in the building for a very long time. And so I went to Carnegie where Emma Bullock helped me run some cathodoluminescence images. And it was a bit of an exploratory study at the time because we didn't know whether pearls would be cathodoluminescent. So cathodoluminescence, for those of you who are unfamiliar, is when you essentially shoot an electron beam at a sample, it can be anything. And in response, the energy from that electron beam produces light, so visible light. And so in this case, it produced green lights and blue lights. And it was able to show us this beautiful detail within the pearl. And if you noted earlier, it looks pretty, boring if you just look at a photograph of it or even a scanning electron image of it, at the micron scale or so, you're really not seeing much. But under cathodoluminescence, there's all this hidden information in this pearl. And so here we have green, which I'm going to take a little sliver out and create a spectrum. So this is the wavelength, which happens to fit the green at around 551 nanometers. And these are just intensity and counts. So if I just look at the green, now we're going to look at it, pretend it's black and white. So this is just a intensity map. And this 551 nanometer thing happens to correlate almost perfectly with the distribution of manganese in our pearl. And so this was really, really exciting because I didn't know that there was manganese in the pearl. It's at very low concentrations. It's barely measurable, but cathodoluminescence allows us to see things that would be otherwise invisible. And so even though it was very difficult to get values, we can see that, yes, there's manganese where there's this green color. Another thing we could try is to look back at that Raman spectroscopy. And so we did organics, just like we did in the last study. So we look at that background fluorescence. And sure enough, we also seem to see various patterns in the overall organics across the layers of the pearl. And so this allows us to think about, well, maybe this manganese could be at least partially bound to organics. So let's now go back to our CL images or cathodoluminescence images and think about the blue side. So on the blue side, we have the secondary hump. So this is still the green, this is the blue. And what does this correlate with? Well, this is what the blue signal looks like on its own without the green in the way. And it looks very different. It's also heterogeneous, but it's very, very different from our green signal on the right. So back to the Raman, we're going to shoot more lasers at it. And I mentioned earlier that the Raman is typically used to look at bonding environments in our crystal structure. So we have, again, our unit cell. And instead of thinking about the unit cell itself and the axis lengths like we did for our coral, we're only going to focus on our trigonal planar groups, which are the carbonates. And so a Raman spectroscopy is a way that we can essentially look at the dance of the molecules. So I like to think of it as we have the symmetric stretch where things are just stretching perfectly in sync. We have this translation where it's moving side to side. We have out of plane bending where it's like really, really bending back and forth. And so each of these peaks represents a different dance. And if we really want to get really crazy, I had done some reading and learned that apparently the ratio of the translation to librational modes can tell us a little bit about the relative orientation of crystallites. And so we know that nacre is made up of these tiny flat pancakes of crystals, right? And so imagine if you have, we know that they're all, the C-axis up, and then A and B could be rotating like this. And so this information from Raman can essentially tell us how much rotation is there in those crystallites over the history of this pearl. And so this is right here. This is the Raman T to L ratio map. And the map seems to be completely anti-correlated with our blue signal, which tells me that the blue signal in the CL is probably due to aragonite structural differences. So this was just a really cool way to think about something that seems to be very simple, right? It's just a pearl. But wow, there's a ton of extra information that we didn't even know was in there. And so we can take this a step further, right? We have these beautiful maps, but we want to see the data. We want to think about what information can we get out of this. So I converted these, essentially each line, into a full line. So we integrated these across the maps to create a 1D line. And so we have the CL for the 551 nanometers. And so each of those white streaks is going to show up as a peak, right? And so we have our nucleus, which is essentially the black hole in the middle. And then we have our peaks. And sure enough, they are mirror images of each other, approximately speaking. You know, it's not perfect, but our pearl is also a Keshe pearl, so it's not perfect. And what I did was then put all of this data together. So not only do we have the original information, which are the oxygen isotopes, but we have CL, we have chemistry, we have Raman, we have fluorescence, we have all this other environmental data. And so this was just a really satisfying way to just see everything all at once. And this is something that's done a lot in environmental work, but it hasn't really been done in mineralogy as much. So I was really excited to show this and essentially combine these different fields together. So let's zoom in a little closer and see what more we can learn. So we mentioned that, of course, we expect temperature to be correlated with oxygen isotopes. So these dark blue dashed lines are those peaks where essentially we're telling it this is where winter is. So low temperatures correspond with high oxygen isotopes of Delo 18. So yes, those peaks say at this point in time, the pearl was making nacre and it was winter out. And we know that the lake gets pretty cold, so. But if we put the data from our cathodoluminescence or our CL data and our manganese data, they don't align with winter. They're slightly offset. And they come a little bit before winter, right? Because the pearl is growing on this side from right to left. And so it's growing in this direction, and there's this consistent offset between the peak for the CL and the peak for winter. And so my theory is that these are fall peaks, and we're getting a lot of manganese right before winter because of this. So in the winter, lakes tend to be stratified, right? And so the winter, the manganese is going to hang out towards the top. But in the fall and in the spring, we get turnover. So the manganese that was at the bottom of the lake is going to come up. It's going to dissolve, go from manganese 4+ to 2+. It'll get incorporated into the pearls, and then the pearls will record that signal. So essentially, we're seeing these different episodes of lake turnover with our manganese and our CL maps. So that was pretty exciting. And so to conclude, I would argue that cultured pearls, not only are they beautiful and used as luxury items, but they can be these really tidy geochemical time capsules that we can use to learn about how environments get preserved in biominerals. So if it works in a pearl, maybe it works in a pearl in nature, right? What if it works in a coral, or it works in a fish otolith? So we're really doing this very basic science to understand how biominerals can preserve these chemical signals. And so in particular, no one had ever really seen lake turnover effects or manganese in pearls before. So this is just a really exciting way to uncover new information from samples that had otherwise already been studied. And finally, I think that we're able to show that using Raman, which is an up-and-coming instrument technology, as well as cathodoluminescence, these are things that we never would have dreamed of using in mineralogy even 10 years ago. And so we're really seeing that we can learn so much more when we combine some of these tools. And so I'm a big fan of really expanding mineralogy and making it relevant to the tools that we have today and making it interdisciplinary, bringing in expertise from biologists and from other fields to help us learn more. And so I hope that you will now have a new appreciation for environmental biomineralogy. And so next time, you think about your bones, or you eat some shellfish, or you go to visit a coral reef, you can think about all of the information that we have yet to learn about these organisms and their biominerals. Also, I hope that you guys like pearls, because I love pearls. And so, of course, this is very interdisciplinary science, and there are a lot of people that are involved with this type of work. And so I have many, many people that I would like to thank for this project, for both of these projects. And in particular, moving forward, I'd like to thank all of my students that are going to be involved and have been involved in these projects. So I mentioned Alice Kojima, but there are many other projects that we're working on currently and in the past that I didn't even mention today. And so I just want you to know, like Yihan Feng, and this summer I have Cecilia and John and Elsie, who are joining me from various institutions. And so we're going to have a very busy summer. We're working on apatite, enamel, and oysters, and phosphorites. So we're going to have a lot of very, very distinct projects, but they all have biominerals in common. And so I know that we're getting close to the end of time, so I do want to make sure you guys get to see the beautiful things that we've entered into the collection. So here are the latest updates, and I'm keeping this short, so I want to really, really give you the highlights today. So first highlight is that this is our current team. So many of you knew Jeff Post and or probably good friends with him. So Jeff officially retired last May. And so I have taken over as the head curator of Gems and Minerals, along with my colleague, Johan Laskew. So we're the two curators currently. And then, of course, we have our collection managers. Russell Feather and Paul Poet have each been at the NMNH for over 42 years, which is absolutely remarkable. And not so far behind, Christine Webb has been a contractor in GEMS. And of course, Mike Wise, who you know very well, has been a pegmatologist with us. And both of them have been around for over 25 years. I think Mike has been around for closer to 30, if not over 30 years. And so we have a ton of expertise on our team. And our newest member of the team is Greg Poley, who is a collections specialist. And so we're slowly training him up to learn things from Paul and Russ. So we have a really, really fantastic group at the moment. It's such an honor to work with everyone on this team. And I know that you know many of them. So we've been going to Tucson now for a couple of years. This last Tucson was a huge success. And I will give you some highlights of things that have come out in the last year or so. So the most recent highlight, so you asked about the news. I have some news. So you may have already seen the stone. This is the line of Marilani that was unveiled last year, but it was unveiled in a temporary case. And frankly, the case did not do it justice. It really just kind of got lost. This is a phenomenal stone. It's a cushion cut Savorite garnet that's 116 carats, precision cut. It's the largest precision cut cushion, square cushion in the world. And so this was a magnificent gift. And today it got a new case 2 weeks ago. So if you haven't been by the museum, please, please come visit us. I mean, this is just a beautiful, beautiful exhibit. So it just unveiled it. And it's at the entrance. If you come from the Mineral Hall into the Gem Hall, you'll see this case. And the stone really just glows in its new home. So that was the biggest news. It took us over a year to get this case made. So that shows you the amount of effort that has gone into this. The other thing that we unveiled recently was the Iris Moonstone necklace. So this is a necklace that was gifted to us by Zoltan David. And it was gifted to us over 6 years ago. And so the designer was a little upset that it was taking us so long. And so when I took over last May, I said, you know what, it's time. We're gonna get this project done. And it took about 6 months from the time I decided we were going to do this till it went on exhibit. And we decided to put it in the moonstone, sunstone, and labradorite case. The reason being, A, there was a really great spot for it. Specifically, there was an old CD-ROM that was to show, how you get color through different structural changes. And so I was giving a tour to a group of second graders, and a little girl raised her hand and she said, "Excuse me, what is that circle with the rainbows on it?" So kids don't know what CD-ROMs are anymore. And so this was very, very outdated. And we decided what better way to feature the new moonstone necklace than to put it in place of the CD. So we got it on exhibit. We're very excited about that. And then here are some recent highlights from 2023. So we got a very beautiful kunzite crystal or spodumene crystal that has these really interesting holes, which I think might have been like due to growth. I don't think they're etch pits. I think they're actually growth pits. And so this is a really beautiful crystal. It stands at about 1.5 feet tall. So it's a very large crystal, and we're hoping to get it on exhibit. We have this cluster of ruby crystals that forms this larger kind of crystal-like structure. This is from Mogok in Burma. This one's probably my favorite. It's an elbite tourmaline, but it's this orange color that we hadn't really seen before. We have some browns, we have some, more yellows, but this orange color was really special. And then this was a star sapphire that was cut in such a way that it actually makes a cat's eye. So essentially they cut it in the wrong orientation or the right orientation, depending on what you think. So that was just a fun addition. We also recently acquired the Rare Gem Butterfly Brooch collection. So this is a gift from our Smithsonian Gem and Mineral Collectors group. And we don't collect jewelry, as you know, so our purpose is never to collect jewelry. But in this case, these butterflies happen to feature very rare stones, many of them American stones. And so we thought this is a wonderful opportunity to showcase American gemstones in a way that the public might actually respond to. Because as we well know, sometimes those rare and beautiful stones are a little small, and the average person would just walk right past them. And so this was an opportunity to get the best suite of bonitoites I have seen in my life. So this was actually made by Buzz Gray, who owned the bonitoite mine. And so he was able to collect all of the bonitoites in these various colors over the course of many years to produce this exquisite butterfly of bonitoites. We also have spessartines from the Little 3 mine in California. So again, only like a true mineralogist or collector would appreciate this. Otherwise, it just looks like a butterfly with, an orange body. And then finally, this is actually the largest cut hiddenite from North Carolina. So that was another beautiful acquisition. And, normally the average person would walk right past this, but in the butterfly, it helps to highlight it. And so we're starting to see the value of having some jewelry in the collection. And of course, we've used this for many years, a strategy of using jewelry to showcase minerals, get people in the door in a more unintimidating way. The Gem Hall is excellent at that. So this will help with that legacy of using jewelry and gems to get people interested in minerals and get them asking questions. And then this was probably one of the more important mineral specimens that we got in 2022. This is Rainbow Mountains is the official name they gave it, elbite tourmaline from Afghanistan. So our collection manager, Paul Powat, and Mike Wise have been trying to get us a really beautiful Afghani tourmaline for many years. And they're unfortunately very expensive. And so this is the first one that we've seen where we loved it, and it was kind of in our price range with our gem group. And so this is just a phenomenal addition. And this is another one that we're hoping to get on exhibit in the next few years. And if you've not been at the museum recently, Mike Wise and Paul actually worked to put together this great exhibit for another exhibit called Cell Phone, Unseen Connections. So this is an anthropology exhibit. It's a temporary exhibit downstairs where they're essentially talking about, the importance of cell phones in our society. But of course, cell phones are made up of elements, and those 61 elements come from minerals. And so this is a great way to collaborate with other folks in the museum. And people just love this case because it shows all of the elements you need in your cell phone manifested as the minerals that they came from. So I really love, they did such a great job with this. So if you haven't been to the museum recently, please come and see this. It's really, really great. And finally, this isn't part of our division of mineralogy, but I have to highlight some of my colleagues in our department. So the OSIRIS-REx mission was a huge success last September. And Tim McCoy, who many of you know, spent 20 years as the PI, one of the PIs on this mission. And so I'm just so incredibly proud of him as my colleague and for the rest of the Division of Meteorites for the successful mission. They essentially flew an spaceship to the asteroid Bennu. They touched the surface with a makeshift vacuum cleaner, essentially, and brought back a capsule. It went back to their Earth, and it was the first sample return mission since I think Apollo 17, I believe. And so it is a really, really big deal. And there was press and media. And what's even more remarkable is that I think it was only 16 days after the capsule touched Earth that we had a piece of Bennu on exhibit for the public. So this was a huge lift for the exhibits team and for Tim and Carrie, Julie, and Kelsey. And so I'm just very, very proud of my colleagues, and it's wonderful to be a part of something like that. So they're currently studying Bennu behind the scenes, and we're just very excited to all be in the same place. And so with that, I'm happy to take any questions, and let's chat about minerals.
Thank you, Gabby. That was fantastic. Betty, can you end the sharing screen?
Oh, I think I can do that too. Let's see. There we go.
Perfect. That was fantastic.
Thank you so much.
Do we have any questions for Gabby? If you want to unmute yourself.
Gabriela, please. Sorry.
Oh, Gabriela, I'm sorry.
Yeah, sorry. I actually don't go by Gabby. I have so many friends that are Gabbies, but my parents were very adamant when I was growing up, so it's so weird for me to be called Gabby. So I go by Gabriela.
Funny because my granddaughter is Gabriela.
Yes.
And it's spelled with 2 L's.
Yeah.
So, but her nickname is Gabby, so sorry about that.
No worries. Yeah, mine is 1 L because I'm actually my family is Chilean, and so we in South America we spell it with 1 L because otherwise it's Gabriela.
Very good. Any questions for Gabriela? Dave?
Yes, I don't know if you can you hear me okay?
Yes.
Okay, I'm when you showed us the photomicrograph of the nacre of the mollusk, is the C-axis vertical in that picture? Is that what we're looking at?
For the most part, yes. So it's essentially the shortest part of the crystal would be the C-axis direction.
So it's actually the narrowest part of the cell.
Yeah, which is so weird, right? Because most minerals tend to grow fastest along the C-axis.
Okay, thank you.
Anyone else? Ken?
Gabriela, can you talk a little bit more about carbon sequestration and how biominerals fit into that picture?
Sure. So I think that's still to be determined, but the idea of carbon sequestration being that there are many ways you can capture carbon from CO2 or potentially carbon that's in seawater, as bicarbonate, carbonate, etc., and preserve it in something that's a little bit less volatile, right? So whether it's organic, so some people, it depends on the time scale we're thinking of. So some people say, growing algae or growing, biomass is a form of carbon sequestration because you're taking out CO2 and forming it into something else. But as geologists, when I think of carbon sequestration, I want something a little bit more permanent. And so thinking about carbonate minerals. And so a lot of people are turning towards like magnesium carbonates, calcium carbonates. The problem is that it's hard to grow some of these crystals through geological processes. It's very energy intensive, it's expensive, You know, you need to pipe things into the ground and you need to have the right chemical conditions. And so we know that biominerals form in different ways than geologically formed ones. And so sometimes just having a biotemplate, you're essentially changing the thermodynamic environment, or at least the kinetics, to make things go faster. And so there is a lot of potential for organisms to essentially make these minerals in a faster, more effective way. But I think that that's something that is still up in the air. So right now we're doing these very basic studies to just understand how they form minerals in the first place. But one of my students was actually looking at leafcutter ants, which is super, super bizarre. And they form almost like a dolomite structure. So dolomite, again, is magnesium and calcium carbonate. And so essentially, rather than just having calcium carbonate, where you would use up all the calcium ions to essentially trap the carbonate, you could use both magnesium and calcium. So essentially, it could have twice the carbon sequestration power. And so thinking about, you know, what makes the ant surface special. And so we looked at various biotemplates, and there's some that can actually produce dolomite, which is really cool.
Gabriela, that was I guess kind of going where my question was with these studies, are people using different chemicals? Like, I guess you just said it with the calcium carbonate, and then there's other ones that are bringing in the magnesium. But like you were talking about the magnesium with the pearl, and how it almost is like a time marker, you know, for when you've got your nucleus and it started to grow to where, what, 2 years later or something, it pulls it out, and then you're doing all your tests between the nucleus and the outer core. And so do they put in, like, I mean, are they using the pearl with any different any different minerals besides the calcium carbonate, the magnesium?
No, so I don't know if you're asking about like whether you could like inject certain elements. Is that like to essentially?
Yeah, kind of like just as an experiment, you know, of different materials and strengths and that sort of thing.
Yeah, so I think there's some work being done on biominerals to try and see if they can form, let's say, dolomite instead of aragonite, right? And so some organisms are very picky and they will only make a certain thing because they are controlling things very strictly. The corals, on the other hand, I mentioned, are more like little beakers. And so they've actually shown that if you put slightly different chemical variations, like they can form calcite instead of aragonite, which is pretty remarkable to me. So in theory, some organisms might be able to form a different mineral given the right conditions. Does that answer your question?
Yeah, I was kind of thinking of graphite and in a way, and sort of in lithium, you know, because they're also like important minerals nowadays, and just the different combinations and what they can show.
Yeah, so most biomineralizing organisms are probably going to try and make the same thing that they normally make. So like graphite would be like very, very different, right? That's a totally different mineral, different chemistry, different structure. So probably not that. But you mentioned lithium, right? And these rare earth elements are really important to, you know, future technologies. And there is some work being done learning about how different carbonates can absorb and take up other elements like lithium. And so we're actually getting a lot more creative as a geological community to think about, you know, where would these deposits be in the future? You know, can we essentially encourage some of these deposits to precipitate or to like get more lithium than they already are, right? And so there is a lot of DOE money actually going towards understanding lithium incorporation in various minerals, biominerals, all kinds of things. So yeah, I think that we're at the very early stages of this kind of rare earth element revolution. And I suspect that in the future, we're going to have a lot more, I hope we get more mineralogists. We need more mineralogists studying structures because there are very few of us left. And I think a lot of colleges, unfortunately, have been cutting their mineralogy programs. And so it's up to people like you and me to encourage universities and anyone you know to ask for those classes. So Barb actually made a good point during her talk. She's like, students, they need to ask for these classes. They need to ask their universities, I need to study mineralogy because I want to study rare earths, right? I want to study these critical minerals. And so it's really up to the next generation to ask for those courses and ask for professors that are going to teach them those things.
That's fascinating. It's just wonderful.
Yeah.
One question. Is there, what is the present state of research on banded iron formations and the cyanobacteria as a cause of some of the oxidation? Is there a lot of research going on still on that, or is that a settled issue?
Yeah, I mean, there's still always research being done, but I feel like that's not as in vogue anymore because we already know a lot about the GOE, and that time period has been very well studied. I am no expert in BIFs, but yeah, I'm thinking more in like modern stromatolites, and a lot of my colleagues, I tend to focus more on modern systems, but
Okay.
I think there's still room, there's always room to learn more. So yeah, BIFs are still important. We love them.
Kathy?
Thank you.
Gabriela, hi. My name is Kathy. I volunteer in the Mineral Gallery
I
specifically.
remember you, yes.
Yes, thank you. So in the Mineral Gallery, it has always bothered me that there's this huge pearl necklace because pearl is not a mineral. However, I think it's a spodumene bauble that it's advertising. But I will say, thanks to your program tonight, I will refer to pearls as a geochemical time capsule.
There you go.
So thank you.
It's a biomineral, right? So they're like
Yes.
going to be minerals. Yeah.
Right. So you opened my eyes. Thank you.
I'm so glad. That's the idea. I think eventually I would love to do, a small corner of the exhibit because most other museums have a biomineral section. We're actually one of the few museums that's a little behind. It would be nice to have like a small section that explains, what are biominerals? Why are they important to you? And also other minerals, right? Like if you go to New York City right now, they recently opened their new mineral hall. And George Harlow did a beautiful job. He has a whole case on clay minerals. It's really great. Like he has ceramics and says, clays are really important for agriculture, for anthropology, and all these connections that we can make with the public that they wouldn't expect, right? So minerals are everywhere. You should never underestimate them. Great.
Very good.
Gabriela?
Yeah.
Yeah, can you hear me?
Yes.
Yeah. My apologies if you mentioned this. If you did, I didn't catch it. Some of the parameters you were talking were delta A over A, delta B over B, delta C over C. I understand that A, B, and C are the dimensions of the unit cells. But I didn't get exactly what is the delta in this context. What is it a difference of?
Yeah, great question. I glossed over it because I didn't want to go into too much detail. So glad you asked. I'm happy to talk about it. So the delta is actually the difference between the measured sample, so the coral in this case, and the average geological aragonite from previous studies. So essentially, I looked at all the literature for all the felt refinements that had been done on aragonites that we knew were geologically formed, and I'm calling that 0, right? So that's like our 0. And then I wanted to see what were the distortions relative to that. Was it longer than geo or shorter than geo? And so the delta is essentially taking your sample minus the geo size.
Okay.
Yeah.
So the A, B, and C are the standard sizes of the unit cells, or are they the sample sizes?
They're the length of the unit cell axes.
Yeah, but the standard average cell.
So the 0 line should be like the standard average
Right.
cell. Yeah.
Okay,
Great.
thank
Absolutely. I'm glad you asked. Love nerding out.
you.
Any last questions? Again, I hope I get to meet you all in person sometime. That would be really lovely.
I
think
have one
Cindy's
more
trying to-
just quick question, Gabriela.
Mhm.
So when I was doing geology, which was a really long time ago, but one of the tools, like I loved your slide with all the toolbox, all your tools.
Yeah.
So what we had in the mineralogy department or the geology department, and then it was mineralogy, and we had a little closet, and in the closet we had a rock saw and to make thin sections.
Mhm.
So do you do that anymore?
We do. Believe it or not, we still do. I had a thick section made by Tim Gooding yesterday.
Oh,
Yeah. But instead of cutting, a typical granite, we had some oyster shells cut open.
nice. Great.
So fear not, we still do old school geology. It's still very, very relevant. So we love it.
Thank you.
Thank you all so much.
Well, thank you very much, Gabriela. That was awesome.
Thank
Oh.
you. Great to see you all.
Really, really nice. Thank you.
Thank you. Stop by the exhibit soon. I hope you like the lion in its new case.
Oh,
can't-
those look fabulous.
Looks fantastic. Well, thank you, everybody. And once again, we have a 2-month break, but we will see you back here in September. And enjoyed seeing everybody and hope to see you over the break. So,
Thank you.
Same here, Kenny. Thanks.
Yep.
yeah,
Thanks, Gabrielle, and
Thank
thanks,
you.
everybody.
thanks, Greg.
Take care.
Good night.
See you all. Have
night.
a good summer.